Hi all, I'm Indu GEVEER, Assistant Professor at Degree School of Engineering and Technology. This is the second lecture on Module 4, Design of Circular Slabs and Domes. Last class we discussed a circular slab with simply supported edge. In this class we are doing a problem on fixed circular slab with fixed end support. So in this case it's very similar to the earlier problem, so I'll just go through it very fast. So here the depth of the slab is also fixed in the similar way. So you get about 125 mm as the depth of the slab. Now the load also, that load will be the same. That will be 25 into 0.125. That is 3.125 kilonewton per meter square. And the load also, the total load will be like what we got earlier, 7.125 kilonewton per meter square. And the factor load is 10.7 kilonewton per meter square. Now the radial moment, the maximum radial moment, sagging moment is at the center. The expression is WR square by 60. So here we get the value as W is 10.7 into R is 2.5 square by 16. Here the value is 4.18 kilonewton meter. So in case of the circumferential moment at the center, this also will be equal to the same 4.18 kilonewton meter. Now at the support, there will be the radial bending moment at the support, that will be minus, that is hogging, 2WR square by 16. So the value is 8.36 minus, that minus represent hogging kilonewton meter, and at the support the circumferential bending moment is 0. Next is the depth check. Depth check you do with the largest value of the bending moment. Here the largest value of the bending moment is 8.36 into 10 raised to 6 by RU. RU is 2.76 into 1000. So this you can do on your own. The next is the area of steel. Area of steel again is a similar way, but the MR and M theta values are different. We got about 4.18 kilonewton meter. Now again we can either use this expression, or I'm here using the SP16 tables. So for that you need mu by BD square. The value comes to around 0.42, and corresponding to that you get a percentage of steel about 0.12, and the area of steel, the minimum area of steel governs. So the minimum area of steel is 150 mm square. So provide 8 mm dia. So calculate the diameter and the spacing as a similar way described earlier. So you get 8 mm dia at 300 mm spacing. 300 is the maximum spacing. According to the maximum spacing criteria, you have to give maximum. You cannot go spacing more than 300 mm. Now this is done. Now next at the support. Actually, ideally the circumferential bending moment at the support is 0, so no need of any rings at the bottom. But at the in the radial direction, you have a hogging moment of minus 2WR square by 16. That value we already calculated. Value at 8.36. Corresponding to that, you calculate mu by BD square. You get about 0.84. Corresponding to that, you can calculate using SP16 tables, PT, and then area of steel. So area of steel comes about 245 mm square. So you provide 8 mm dia, convert into diameter and spacing at 200 mm center to center. Very similar way I told earlier. Now we already checked for minimum steel. Check for minimum steel and find the spacing and diameter that we've already done. Next is a check for shear. Check for shear is exactly the same as like a simply supported circular slab. So I won't be doing the calculations here. So next, let's do the detailing. For detailing, first let me consider the bottom plan of the circular slab. This is the bottom plan. Bottom plan we gave as for radial and circumferential direction. moment, we got vertical and horizontal steel. That is, we got it as 8 mm at 300 mm spacing, both vertical and horizontal. 8 mm dia at 300 mm center spacing. Now here we don't actually require a circumferential reinforcement, but still it's a good practice to give at least 2 rings of circumferential reinforcement. Now from seeing the top view, this is a fixed edge, so we need top reinforcement because there is hogging moment. So we already calculated that reinforcement. It should be provided in the radial direction in the top. Okay, so we got this as 8 mm dia at 200 mm spacing. Now we may need to give a circular to at least 2 circular ring to tie this reinforcement. Now let's look at the sectional view. We provided the depth of the slab as 125 mm and we give the bottom steel as 8 mm dia at 300 mm spacing. Same here also. Now we gave the top reinforcement that should get, you should insert it into the, for full development length into the support, because there is a hogging moment here, the maximum moment is at the support, so you have to have full development length inside, and this length can be around 0.25 d. In this case it comes around 1250 mm. Now to tie this reinforcement, you have to provide some rings, at least 2 rings. Next topic is domes. Dome is a shell structure generated by revolution of a regular curve about one of its axes. So if we consider a spherical dome is created by a revolution of a segment of a circle about the vertical axis. So if you rotate this, revolve this segment of a circle about the vertical axis, you get a figure somewhat like this. This is the picture of a spherical dome. And in case of conical dome, it is created by a segment of a right angle triangle. So if you revolve it around the vertical axis, you get a figure like this. So this is called it is a shape of a cone. And the important point is here domes are primarily subjected to only axial forces. The bending moment and shear forces in domes are negligible, and then we can, and this is the reason we can reduce the steel requirement compared to normal slabs. And domes are commonly used as roof for circular areas, circular water tanks, or planetariums or big exhibition halls. Domes can be constructed using masonry or even reinforced concrete for larger spans. Spherical domes. Spherical domes we already saw. It is formed by the revolution of a part of a circle over its vertical axis. And it can be considered as several rings. These are several rings that is placed over another. And the circle of each ring is called the latitude. And the circle passing through the crown, this is the crown. Crown is the topmost point, and connecting with that diametrically opposite point. If you connect with this point and the crown and extend it to the diametrically opposite point, then that line is called a meridian. Okay, so in this figure you can see this is called the meridian and this is called the latitude. And there are two types of forces that act on a dome. One is the meridional thrust. Meridional thrust acts along the meridian direction. That is, it is shown here. This is the meridian direction. You can see that is represented as T, meridional thrust. And the second is the hoop force. Hoop force is along the latitude direction. That is represented like this. This is hoop force. And it is represented by H. Meridional thrust and hoop force. Now let us consider the spherical dome subjected to uniformly distributed load. We already saw that there are two kinds of forces. One is the meridional thrust that is acting along the meridian, and hoop force that is acting along the latitude. The meridional thrust at any point P. So this is the point P at an angle theta from the vertical can be derived as T is equal to WR by 1 plus cos theta. Similarly, hoop force can also be derived as this is the expression WR into cos square theta plus cos theta minus 1 divided by 1 plus cos theta. And hoop force is maximum. If you see this expression, if you solve this, you will find that the hoop force is maximum when theta is equal to 0, and the maximum hoop force is WR when theta is equal to 0, cos 0 will be 1. So the maximum hoop force will occur at H, will be at the crown, and the value will be WR by 2, and the value is plus. That means it is compressive. That means hoop force is compressive. So it is hoop compression. And if you want to convert the hoop force into hoop stress, you divide by T, the thickness of the dome. So WR by 2T will be the stress, hoop stress at the crown. That is the maximum hoop stress. Now at the crown is the maximum value of hoop stress. Now what happens when theta is at this point, it is maximum. So when theta keeps on increasing, the hoop force decreases. So theta increases, hoop force decreases, and at one point the hoop force becomes 0. That is when this cos square theta plus sin square theta minus 1 is equal to 0. So if you solve this, at theta is equal to 51.8 degrees, the hoop force is 0. Now what happens when theta is greater than 51.8? When it is greater, the hoop force becomes negative. That means the hoop force becomes tensile. So it is important to note at the crown, the hoop force is maximum, it is compressive, and when theta increases, the hoop force reduces, and it reduces to 0 at theta is equal to 51.8 degrees. And then if theta is more than that, then hoop force becomes negative and it will be tension. The next case is the dome is subject to a concentrated load at the crown, W. So in this case, the expression can be derived for meridional thrust. T is equal to W by 2 pi r sine square theta. And hoop force also, that will be minus W by 2 pi r sine square theta. This minus indicates that the hoop force is tensile throughout. That means wherever you go, there will be a tensile hoop stress. Sine hoop force is maximum at the crown. Theta equal to 0. Theta equal to 0, what happens? Theta is equal to 0, sine 0 is 0. So hoop force will be infinity. That means if it is a load at a single point, then the hoop stress will go to infinity. So it's always preferable that you divide. Your concentrated load should be spread over a larger area. So the hoop force is always negative, indicating that the force is always tensile. Now, if you want to convert into stress, you have to divide by the thickness of the dome. So W by 2 pi r T sine square theta. In case of wind load, usually it's very tedious to analyze a wind load. So therefore, 1000 to 1500 Newton per meter square is usually added on the surface as UDL to consider the effect of the wind. And minimum thickness of the dome usually provided is 75 mm. And steel has to be provided in both the direction, meridional direction and the latitude direction. We already saw the stresses in the meridional and the latitude direction. Hoop stress in the latitude direction and thrust, meridional thrust in the meridional direction. So steel has to be provided as given in the figure. And in the top, you have to provide a mesh reinforcement. This is because if you extend the meridional reinforcement to the top, there will be a lot of congestion of reinforcement. So instead of that, you stop somewhere in between at the top and then give a mesh reinforcement as the top. Now, as the forces are only axial forces, which I already mentioned, there is no bending moment and shear force in a dome. The steel can be provided exactly in the middle of the thickness of the dome that we'll see later. Now, the provision of ring beam. In case if the dome is not hemispherical, that means this is a perfect hemispherical dome. That means at this junction, the tangent is vertical. If it is not hemispherical, as this case, what happens is the meridional thrust will be inclined at the base of the dome. So this is the base of the dome. At the base of the dome, the meridional thrust will be in the tangential direction. So it will be inclined. So because of this, it will have a horizontal component. So this is the horizontal component of the meridional thrust. This will create a force on the supporting wall. So there will be a wall that is supporting the dome and it will create a force, horizontal force on the wall, and the wall may burst outwards. To avoid this, a circular ring beam is provided at the base of the dome, which is designed to take the horizontal component of thrust. So as shown in this figure, you provide under the dome, you provide a horizontal ring beam. That means if you see the elevation, you can see it like this. But if you see the plan, the ring beam will be circular. Okay, and the horizontal component of the thrust will act like a force on the ring beam in the radial direction. Okay, due to this force, the circular ring beam will be subjected to a hoop tension. So there will be a tension in the ring beam, and the ring beam has to be designed to take this tension. And the provision by providing the ring beam, only the vertical reaction is transferred to the supporting wall. So the supporting wall is below the ring beam, and the horizontal force component of the thrust will be taken by the ring beam, and only the vertical component will be passed on to the supporting wall. By this way, the wall will not burst outwards. Now let us do a problem. Design a top dome for a span of 13 meters. Assume the rise of the dome as 1.7 meters. Live load of the dome is 1.5 kilonewton per meter square, and use M20 concrete and Fe415 steel. Also design the ring beam. Now let us draw the geometry of the dome first. The span is given as, this is the dome, and the span is given as 13 meters. And the rise of the dome is given as 1.7 meters. And first we have to find the radius of the spherical dome. So the radius is not 13 by 2 because the center of the dome is going to be somewhere here. Okay. So this distance will be the radius of the dome. Now to find the radius of the dome, we have to use the Pythagoras theorem. Now you look at this distance is also the radius. Right? So now let us use the Pythagoras theorem. Take this right angle triangle. Okay, and use the Pythagoras theorem. We know this rise is 1.7 meters. So remaining this distance will be r minus 1.7. Okay. Now by using the Pythagoras theorem, we can find out r square is equal to r minus 1.7 whole square plus 13 by 2 whole square. This distance is 13 by 2. Okay, so by solving, we will get the r as 13.27 meters. Now let us find this angle. Let it be phi. So we can use the sine rule. Sine phi will be equal to 13 by 2 divided by r. Radius we already found, it is 13.27. So by solving this, we'll get a phi is equal to 29.3 degrees.